Hello students, and welcome back to another algebra video. You know what to do. Pause the video, try this problem in your notes, and then unpause it to do it with me. Okay, solve the system of linear equations by elimination and check your solution. So the first thing I'm going to do when I hear the word elimination is I'm going to look at my like terms. I'm going to look at my x's. In order for these to have the opposite coefficients, I would need to multiply the top equation by -3. I would need to multiply by -3 so that I had -3x and +3x. Okay, so that's if I want the x's to cancel. Let's look at the y's, see if that's easier. Well, I have 3y in the top equation, and I have y on the bottom equation, so I would need to multiply the bottom equation by +3. If I want the y's to cancel, I would need to multiply the bottom equation by +3, because I already have -3y, so I would want +3y on the bottom. Now, what we need to ask ourselves is what's going to be easiest? Is multiplying the top row by -3 or is multiplying the bottom row by 3 going to be the easiest? I think you know what I'm going to say. I like positive numbers, so let's multiply the bottom. And we will do just that. We're going to take the bottom equation, 3x plus y equals 12, and we're going to multiply it all by 3. So 3 times 3x is 9x. 3 times y is 3y. And 3 times 12 is 36. Wonderful. Now what I'm going to do is I'm going to write my equations. Equation number 1, we haven't changed equation number 1. It's still the same. X minus 3y equals 24. And now my new equation number 2, 9x plus 3y equals 36. Now, look at that. My y's are all ready to cancel. I just need to add the equations together. X plus 9x is 10x. The y's go away. They are eliminated. And I have 10x equals 24 plus 36 is 60. And then, oh hey, if I divide by 10 on both sides, 60 divided by 10 is 6. Nice and easy. So now I can take this x equals 6 and I can plug it into any equation that I want. Equation number 1 or equation number 2, and I can solve for y. Now I notice the bottom equation has y with a coefficient of 1. So if I used equation number 2, I wouldn't need to divide at all when I'm solving for y. So let's do that. We have 3x plus y equals 12. But I know that x is 6. So I have 3 times 6. That gives me 18 plus y equals 12. And if I subtract 18 on both sides, I get y equals 12 minus 18 is -6. Let's check that answer though. 12 minus 18, yeah, -6. Okay, beautiful. So I have x and I have y, which means that my final answer is x, comma, y, or 6, comma, -6. And look at how colorful our opening screen is. I love it. Okay, let's move on to what we have for today. Today, we're going to talk about section 5.4. 5.4 is solving special systems of linear equations. Ooh, what makes a system of linear equations special? We're going to learn about that today. So, our learning target for today is I know the types of solutions a system of linear equations could have. So the types of solutions has something to do with whether or not it is a special system of linear equations. And our success criteria is I can determine the number of solutions a system of linear equations has. Interesting. The number of solutions, I thought it had one, right? Every problem we've done in 5.1, 5.2, 5.3, it's always been one. So the number of solutions, interesting. Before we talk about the number of solutions, let's review what is a system of linear equations. It is a set of two or more linear equations. Except remember, we're not talking about the or more part. Set of two linear equations in the same variables. So we're going to continue working with these today. And what is this about the number of solutions that a system of linear equations could have? Well, when we think about the solution of a system of linear equations, remember back to 5.1, we saw that the lines cross. That the system of linear equations, it's two lines, right? Because they're linear equations, I have two lines. Let's write that. Two linear equations means two lines. So in 5.1, we actually found where is the point that these lines cross. That's the solution. That's still the solution in 5.1 and in 5.2 and 5.3. We just didn't graph them. We solved it in a different way other than graphing. But if we graphed them, we would see that anytime there is one solution, one point, x comma y, it's where the lines cross. Now, what would happen if my two equations, my system of equations, what would happen if they were the same line? Like they had the exact same slope. Oh, whoops, sorry. If they had the exact same slope, I'm sorry, not if they were the exact same line, but if they had the exact same slope, well, then the lines are parallel. Do parallel lines cross? Remember back to section 4.3, parallel lines don't cross, they never intersect. So then there would be no solutions because the lines never cross. The lines never cross. So, never cross. The point where they cross is the solution, so there can be no solution if they don't cross. Alright, now what happens if the lines are exactly the same? They have the same slope, the same y-intercept. What happens then? Then they are the same line. Like there's two lines, but they're the same. So there really is only like one line. Like they're on top of each other. It's like take this blue line as one of them, and then the black line that I just drew, that's another one of them, and they're literally like they're right on top of each other. So they are always, every point on this line is a solution because they cross at every point. And when I say every point, how many points are there on a line? Well, lines extend forever in both directions. Lines, that's what these arrows mean. It just keeps going and going and going and going. So there's infinitely many solutions. We can't even count how many solutions there are. There's infinitely many. Well, I guess it could be countably infinite, so never mind. We might be able to count it, but it would take an infinite amount of time to count. So there are infinitely many solutions. And there, if you're wondering, there are different sizes of infinity. There's countable infinity and an uncountable infinity. You'll learn more about that if you take math classes in college, but we're not going to talk about that here. So there are infinitely many solutions when the lines are the same line. So, great, Mrs. Dodge. This sounds good. This makes sense, but I have a question for you. How do I know if this is the case? Like, do I always have to graph it then? No. What a good question. I'm so glad you asked. Let's see an example, and we'll find out. So first, because these are already in y equals mx plus b form, let's graph these. And let's see how many solutions they have. So if I graph equation number 1, let's see, the y-intercept is 1 and the slope is 2. So I go up 2 over 1, and here is my line for equation number 1. Now, if I look at equation number 2, my y-intercept is -5. Oh no, -5. I don't have enough space. 1, 2, 3, 4, 5. -5. And my slope is 2, so I'm going up 2 over 1. Then, here is the graph of my line. Wait a minute. It doesn't look like these are going to cross. If the lines don't cross, if they are parallel and the lines don't cross, there is no solution. Now you might have seen that in the title of the example it says no solution. And there are many ways that we can tell that this system has no solution. One is if I graph them, they don't cross. They don't cross. That's one way to tell that there's no solution. I can also just look at the equations and see they have the same slope. Same slope equals parallel. So I know that they're never going to cross. I don't even need to graph them. I can just look and say, boom, slopes are the same, they're parallel, never cross, the end. No solutions. Also, I could say I didn't want to graph. Say I forgot how to graph, or I just don't want to. Let's solve this by substitution. So no matter how you choose to solve this, you're going to get no solutions, and I'll show you how. If we solve this by substitution, I have y equals 2x plus 1. So I'll substitute that into this equation. We have 2x plus 1 equals 2x minus 5, because both of these things are equal to y. All right, now let me solve this. I need to get all of my x's together. So I'll subtract 2x from both sides. And then, oh wait. Oh, I get 1 equals -5. Wait, so both of the 2x's disappeared. When I subtracted 2x, they both disappeared. They both canceled. And I get something that's not true. 1 is not equal to -5. That's not possible. Now, you might remember this back in chapter 1 when we were solving linear equations, and we would get things that weren't true, and we would say, oh, this means no solutions. If I get something that's not true, it means that there can't be any solutions, or that no solutions exist. So, it doesn't matter how you want to do this. You can see that they don't cross. You can see that they have the same slope. Or you can start, you can do substitution or elimination. No matter what method you use, you're going to find a problem. You're going to find that there are no solutions. Let's go ahead and check our answer. Yup, they graphed as well. Lines have the same slope, different y-intercepts, so the lines are parallel. So there is no point that is a solution. You can also go by substitution. You get something that's not true, so there is no solution. Awesome. They did the same thing that we did. Awesome. And oh yeah, this is a fun fact. A linear system, a system of linear equations with no solution, is called an inconsistent system. And you'll learn more about that. There are inconsistent matrices and things, dependent matrices in linear algebra. So if you like chapter 5, keep taking math classes. You can take linear algebra in college. Let's do another example. We saw, one solution. We saw that all over in 5.1, 5.2, and 5.3. In the last example, we saw no solutions. Now, what does it look like to have infinitely many solutions? So let's do the same thing we did last time. Let's graph first, and then we'll take a look at the system and see if we could have seen it from the system. Because last time we looked and we saw, oh, they have the same slope, must be the same, must be parallel, so no solutions. So let's see if we can do that with this. And then we'll try substitution or elimination and, see what happens there. So first let's graph. And to graph, let's put these in y equals mx plus b form, because right now these are in standard form. So if I solve equation number 1 for y, I'm going to add 2x to both sides, get y equals 2x plus 3. If I solve the second equation, I need to add 4x to both sides, 2y equals 4x plus 6, and divide everything by 2. So we get y equals 2x plus 3. Those are the same line. Oh my. So what will happen? Let me clean this up a little bit. What will happen when I graph these? If I graph the first equation, I go up 3, and then my slope is 2, so I go up 2 over 1. Like this. And if I graph equation number 2, my y-intercept is 3 and my slope is 2, so I go up 2 over 1. Oh my goodness. Oh my goodness, they're the same line. And remember, if I have the exact same line, like 2 of the exact same line, like right on top of each other, it means that there are infinitely many solutions. Now, when we solved for y, when we took these and we put them in y equals mx plus b form, we noticed that, oh yeah, hello, their equations are exactly the same. But if we look at this system over here, I can see that if I multiply the top equation by 2, I get, let's see, well here, so 2 times the top equation, 2 times negative 2 is negative 4x, 2 times y is 2y, and 2 times 3 is 6. And look at that. Look at this. What I just got is the exact same as equation number 2. So equation 1 is the same as equation number 2. It's just been like divided by 2, basically. If I take equation number 2 and I divide it by 2, I get equation number 1. So these lines are actually the same lines, and this has something to do with those dependent matrices that I was telling you about before. So you'll have to take linear algebra in college if you want to know more about that. Okay, so the last way that we could see this, if we want to, and we have time, so let's do it, is if I decided that I want to solve the system using elimination. So I say, I look at my y's and I say, oh, if I multiplied the top equation by negative 2, I would get negative 2y on top, and that would be the opposite of 2y. So let's do that. Let's multiply the top equation by negative 2. Negative 2 times negative 2 is negative 4x. Negative 2 times y is negative 2y. And negative 2 times 3 is negative 6. So this is our new equation number 1. We haven't touched equation number 2, so we'll put equation number 2 underneath it. Negative 4x plus 2y equals 6. And look at that. The y's are the opposites. They're ready to cancel. And they are eliminated. Now, whoopsie, I just noticed I multiplied wrong. -2 times -2 is positive 4x. So that should be a positive 4x. And when I add 4x minus 4x, wait, oh, that's actually eliminated too. Whoops. So that's 0, and the y's are gone, equals -6 plus 6. Oh, that's 0 too. Oh, so I get 0 equals 0. Hey, think back to chapter 1 when we looked at solutions of linear equations, not a system, outside of a system. When we looked at linear equations, if we got something like this, some equation that was always true, 0 equals 0, that is a true statement, it means that we have infinitely many solutions. So it doesn't matter if you graph it, it doesn't matter if you notice that, oh, if I divide equation number 1 by -2, or equation 2 by -2, I get the same thing as equation number 1. It doesn't matter if you solve for y and see that they're exactly the same. Doesn't matter if you solve by elimination. Whatever you do, you're going to notice, you're going to see that there are infinitely many solutions. So, let's check and make sure that we were right. Graph, yeah, same line, infinitely many solutions, all points on the line are solutions. Or we could solve by elimination, we get 0 equals 0, so has infinitely many solutions. Boom. Okay, it is that time of the video. It is time to assess your understanding. And I need a color other than black if I want you to see this. So, where are you on a scale of 1? Well, now it's too hard to see. On a scale of 1 to 3, where are you in your understanding of our learning target and success criteria? Do you know how to tell if a system of equations has 1, none, or infinitely many solutions? Do you know what that means, like visually, and do you know how to find that? If you don't, it's time to ask some questions. If you're getting there, it's time to try your homework, and if you think you totally got it, it's time to help the people around you. See if you can help your friends or other people with their homework. And here are some practice problems that you can try to practice the skills that you have learned in this video. Oh, and more practice problems, yay! So much practice, it's wonderful. And as always, let's end our video with a launch, shall we? Today's launch is from Emma Watson. She's Hermione. And Belle in the live-action Beauty and the Beast. Oh, love Emma Watson. And she says, I'm not going to school just for the academics. I wanted to share ideas, to be around people who are passionate about learning. What are you going to school for? Emma Watson's going to school not just for the academics. Academics are part of it, but she also wants to share ideas, and she wants to be with people, with other people who are passionate about learning. What are you going to school for? Do you want to go to college and make a better life than maybe what your family has right now? That was me. That was me. Are you going to school because you have to? And you don't really care, but you have to, so I guess I'll show up? Are you going to school because you want to make your family proud by being the first one to graduate? What are you going to school for? What you are going to school for will change the way that you treat school, the way that you think about school. If you are here because I want to get into a good college and get a good job that, pays a good amount of money, that I can support my family, and I don't have to worry about, whether or not we can afford this or that. That was my family growing up. And if that's your motivation, you know, you're a little more motivated maybe to do your homework and to do well and to really learn what you want to learn, because you know the stuff that I'm learning in some of these classes eventually I'm going to need to use in my future. I'm going to need to, you know, jump through the hoops for high school, take the classes that I have to take that maybe I don't enjoy, so that I can get into that college and I can do well in that college. If you're going to school for the friends and you're solely focused on the friends, maybe, you know, your academics, your grades, you know, slip to the side a little bit. If you're going to school because you have to and you don't really care, maybe you fail a couple classes and you don't really get good grades. So my challenge to you is, what are you currently going to school for? What do you want to go to school for? There's got to be some reason deep down that you want to go to school, either whether it be for the friends or to have a nice job in the future, making connections with people so that you can network, get the jobs that you want in the future. What do you want to go to school for? What makes you want to come to school? And if you can find something that makes you want to come to school, it'll be easier to get yourself out of bed, to get into school, and maybe to, you know, try a little bit harder on your homework and get better grades. So I would encourage you to think about, what are you going to school for? Do you want to share ideas? Do you want to be with people that are passionate about learning? How does one become passionate about learning? I hate school. I hate having to do homework and everything. How are some people passionate about it? Ask those people. Or think, get inside their head. What would make someone passionate about learning? All things to think about. But the main takeaway is, I would encourage you, what do you want to go to school for? And if you can find a reason that makes you want to go to school, it'll be easier to tolerate school. That is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day. And thanks for being here. Thanks for watching. Bye.